Good morning, everyone, from Berlin, Germany. The topic of my talk today is going to be native large object support in Git. The focus will be mostly on ongoing projects that will eventually help Git to become better at storing large binary files. Let me first introduce myself. My name is Patrick Steinhardt. I started diving into Linux in 2002 when I was 11 years old. I became an open source contributor in 2011. I'm a Git and libgit2 contributor starting in 2015, backend engineer at GitLab since 2020, and manager of the Git team at GitLab since 2024. My passion project in Git for the last 2 or 3 years was upstreaming the ref table backend, which is an alternative way to store references in your Git repositories. Somehow, this also brought me the nickname Steiny the ref table guy. But today, I'm happy to finally be talking about something different than ref tables. I already did 3 presentations about that topic, so I'm really looking forward to finally talk about something else. Before we jump into the nitty-gritty details, let's first talk a little bit about the problem space that we're operating in. The foundation for all of what we're going to talk about today is the Git object model. This will probably be familiar to most of you, but it's helpful to revisit the core concepts. All of your data in a Git repository is stored in objects. There are multiple different object types. First, the commits store history and how it evolves over time. They store the commit message as well as the metadata about the author. Second, each commit points to a tree. You can think of a tree like a directory. Just like a directory contains entries pointing to subdirectories and files, trees have entries pointing to other trees or blobs. And finally, we have the blobs themselves, which basically contain your actual data, like for example, your code. These blobs will be our main focus for today. Now we know a little bit about the theoretical object model of Git. So let's explore how Git stores these objects on disk. So let's first create a new repository. In theory, all the objects would be stored in the .git/objects directory. In practice though, at the current point in time, we don't yet have any objects, so there's nothing much to see here. To make this a little bit more interesting, we can thus create a new file and stage it. As part of that command, Git writes the file to the object database as a blob. The new object is stored as a loose object, so it is a standalone file that contains the complete contents of that object. The file is stored in a sharding directory called 32. These sharding directories are basically used so that no single directory needs to store too many different files at once. The contents are then stored in the file starting with 3FAE. The full name of the object can be derived by concatenating the 2 hexadecimal digits from the sharding directory together with the file name. The name of that object itself is derived from its contents. This is what people basically mean when they talk about Git being content addressable. Given the content of an object, you can derive the name of it. So if you want to reference the object, you can, for example, use git cat file with the object name to output its contents. Speaking about contents, let's also have a look at the on-disk format of the file itself. At first, this doesn't really make too much sense. This is because Git compresses all of its objects using the zlib format. So to make this a little bit more insightful, we can, for example, use a tool like pixz to output the object contents. The loose object format is kind of trivial. We first have a type prefix, which can be anything like blob, tree, commit, or tag. That type is followed by the size of the object, and the header of the object is then terminated with a null byte, and where the remainder of the object contains the actual data of it. I'm not going to go into the specific formats of all the different object types that we have, as those aren't really relevant in our context of large binary files. Your files are always stored as a blob, and their format is somewhat trivial. Over time, your Git repository will accumulate more and more loose objects. Every time you add a file, delete a file, create a commit, edit a commit, or really do anything that ends up in the repository's history, you end up writing at least one new object into the object database. If we, for example, create another commit, we'll end up writing 2 more objects. First, the tree that connects the blob with the file name, and the commit that stores the metadata like the message authorship information and references to any parent commits. It's quite common that projects like the Linux kernel, for example, have millions of objects. We don't really want to store each of these objects as separate files. It would mean that we have to do many thousands of syscalls every single time you want to read or from or write to the repository, even in a medium-sized repo, and that just doesn't scale well. Furthermore, we would lose the opportunity to save storage space. While loose objects are zlib compressed, this compression only allows us to save storage space within that single object. But Git histories usually consist of lots of incremental changes to a slowly increasing number of files. So ideally, we should also be able to store these incremental changes in a more efficient way. This is where pack files come into play. Instead of storing every loose object as a separate file, we put them into a pack file. This pack file allows us to reap a couple of benefits, which I'll explain in a bit. First though, let's ask Git to create such a pack file. You don't really have to execute this command yourself under normal circumstances, as Git knows to pack objects during automated repository maintenance. You can see that after the repack, all of the loose objects are gone. Instead, we now have a single pack file that contains all of our objects. It's kind of obvious that the .pack file contains our objects, but what is the .idx file? As you've probably guessed, this file acts as an index for our objects. This allows us to immediately figure out which objects are contained in its corresponding pack, but it also allows us to derive additional information to speed up object lookups. We can have a look at the index by using git verify pack with a -- verbose flag. This outputs a bunch of information that is encoded in the pack file index. It contains the object type, the inflated object size, the size of the deflated data in the pack file, as well as the offset into the pack file where that specific object is stored. Furthermore, all the object IDs are sorted lexicographically. Equipped with that information, we can thus easily look up an object by first doing a binary search in the index for the desired object ID. We then extract the size and the offset of that object, map the pack file into memory, and finally we deflate the object data at that given offset. So this allows us to quickly access a bunch of objects without doing a ton of syscalls. And the operating system manages reading the data from disk because we have mapped the whole pack file into memory. But this still doesn't really solve our other problem. How do we efficiently store small incremental updates to our objects? You may have spotted the answer already in the output of git verify pack, and the answer is deltas. To demonstrate how deltas work, we first create a somewhat large file and commit that file. Next, we append a single additional line to this file and commit again. Ideally, Git would not store that large file twice, but instead store only the base file and a delta that only adds the last line. So let's do another repack. As you can see now in the last line, Git mentioned that it has written 9 objects into the resulting pack file, one of which is represented as a delta. So let's have another peek at the generated pack file. At the bottom, we can now see that we have 8 different objects that are stored as non-delta objects. But in addition to that, we can also see that we now have something called a chain length, where we have a single object with a length of 1. This already hints at something. Deltas don't necessarily have to apply directly on top of a full object. Instead, they may also apply on top of another delta, so that you can rebuild the original object by first taking the base object and then applying all deltas in the chain to get to the desired shape. But let's get back to our simple case for now. We can easily spot our original file and the incremental change. The original file is stored as the full blob that is almost 4 kilobytes in size. The deltafied change is the second highlighted one in this listing. The delta specifies the base object that it applies on top of, and furthermore, we can see that it only has a size of 7 bytes in total, which is overall quite a saving. I'm obviously skipping over a lot of the details now, but this short intro should have given you a rough idea of how Git stores its objects. We'll need some of that knowledge as we start to dive into the main topic of today, which is large binary files. Git is infamously bad at storing large binary files in a repository, which isn't really entirely surprising. Git has been designed to store source files or other text files, and it really knows to store those in a very efficient way. zlib compression helps a bunch with structured text, and the deltification we use in pack files allows us to handle many incremental changes very well. But once the files are large and unstructured like binaries, the design starts to fall apart. Modern best practice is thus to never really store binary files in your repositories. The first problem I want to talk about is deltification. The deltification algorithm that Git uses can do wonders for text files and significantly shrink the overall size required to store them. But the algorithm isn't really well suited for binary files. To showcase the issue, we first create a 500 megabyte binary file with some random data and commit it. Next, we append another 10 megabytes to that file and commit again. The expectation is that when repacking these files, we should see a delta so that we don't have to store the whole blob again. And yes, as we can see with Git verify pack, that is actually the case. So maybe it's not that bad. Well, let's repeat the exercise again and append another 10 megabytes to that file and repack. You'd expect that we are again able to store this change as a delta, I guess. But if you thought so, then you're wrong. We now store 2 full copies of the blob and only 1 delta, so the resulting pack file is around a gigabyte in size. The problem here is that computing the deltas for large files is somewhat expensive. Very simplified, the deltification algorithm first sorts the objects by object type and size, so that objects that are likely to be similar to one another are close to each other. We then use a sliding window through these objects. Inside that sliding window, we then compute the delta between each of the objects with one another. And once we've done that, we pick the best delta in that window. Now, computing these deltas is reasonably fast with small files, but computing them with large binary files is way too expensive. Git thus has a certain threshold at which it stops deltifying objects completely. And as we've seen in the example, that threshold is 512 megabytes by default. So beyond that size, Git is unable to save any storage space for you. And even before, it's already very inefficient. Let's move on to the next problem, repository history. Whenever you clone our Git repository, you'll by default get a full copy of all of its history. This is also basically what you want in almost all the cases, especially when you work with repositories that are at most a couple of gigabytes in size. But once we start talking about large monorepos with binary files in them, this changes quite significantly. You probably don't want to download a full 300 gigabyte repository. Also, it doesn't really help that Git does not support presumable clones. So if you're 280 gigabytes through the download and then your network hiccups, then you're probably going to have a very bad time. Git already has tools to solve this via partial clones, where you can tell it to, for example, not download any blobs larger than a certain threshold. But those tools aren't automated, and thus the user needs to know how to wield them. Furthermore, once you have downloaded such large files, Git also does not know how to prune them again in case a large binary hasn't been accessed for a while. Of course, large monorepos don't only cause issues on the client side. Code forges are also struggling with them. A code forge does not really have the luxury of partial clones. It needs to have all the objects available, as it would otherwise not be able to serve those to the client. This results in a bunch of problems. First, these large objects cost tons of disk space. Our analysis on GitLab.com has shown that 75% of our storage space in Git repositories can be attributed to binary files that are larger than 1 megabyte. Second, repository maintenance is really expensive, as we have to somehow wrestle with those large objects. And third, we're not really able to offload any of the traffic to a content delivery network. All traffic needs to be served by the Git server, which can quickly exhaust our resources. So overall, large objects are a significant cost factor for any large Git provider. Now, these problems are known for a long time already, and Git users have adapted to work around those shortcomings. We have ended up with a couple of different band-aids which either require the user to change or that require to use external tools. The number one band-aid to this problem that the Git community always keeps telling our users is to just Git better. Common wisdom says that friends don't let friends store binary files in Git repositories, and if you do that, you're holding it wrong and really should rather go back to Subversion. Of course, there's less drastic methods compared to going back to Subversion, and nobody really wants to do that. You could, for example, use an artifact repository to host binary files, or use proper build systems that fetch the dependencies for you. And in a lot of situations, this might even be the correct answer indeed. But ultimately, we're merely working around the limitations in Git. The next best band-aid then is to tell our users to use something like Git LFS. Let me first be clear. Given the limitations that Git LFS has, it's a very well thought out tool and also does a very good job. The main reason I consider it to be a band-aid only is that it is not a native part of Git itself. The way that Git LFS works is that you configure a number of path patterns in Git, matching, for example, all of your Linux ISO files. When a file matches, we don't store the file's contents in Git. Instead, we only store a pointer to that file. When checking out that pointer, Git will know to download the actual file from the Git LFS server and put it into your working tree instead. Furthermore, when committing such a file, then Git LFS will instead commit such a pointer and upload the actual binary file to the LFS server. So Git LFS solves a lot of the problems with binary files, and it's mostly easy to use and also to set up. But it also creates new problems. Git LFS is not part of Git itself and needs to be configured separately. Each LFS object needs to be downloaded as a full copy. It is not able to transfer only the delta, for example, between the old and new state of a binary. And also, it does not have any answers to binary files that you may have added to your repository by accident. Those are stuck in history, and you need to rewrite the repository if you want to fix that. So tools like Git LFS and similar tools like Git Annex solve some problems, but not all of them. So we've now taken some peeks into the problem space, why Git doesn't handle large binary files well, and at some of the band-aid solutions. But the purpose of my talk isn't only to complain about the status quo. Instead, we want to propose solutions and ways for us to solve some of the problems we have just outlined. In fact, those aren't only proposals. GitLab and the Git community is actively working on those solutions already. The first part I want to talk about is partial clones. Git already supports partial clones for quite a while. When cloning a repository, the client specifies a so-called object filter. This filter tells the server which objects it should exclude so that the transferred pack file does not have them. Those objects are promised to exist by the server so that the client can fetch them at a later point in time as needed. You can ask for such a partial clone by saying git clone -- filter. There's a bunch of different filters, but in our example, we exclude all the blobs. You can see that as a result, we actually perform two fetches. We first do a normal fetch that includes all the non-blob objects, and then as we proceed to checking out the commit, where Git discovers that it doesn't have any of the blobs and performs a backfill fetch to download all blobs required for the checkout itself. Every time you now want to reference an object that doesn't exist, Git will download it on demand for you. The result of such a partial clone is a significant size reduction. A normal clone of that repository, of that specific repository, is 2.8 gigabytes, whereas the partial clone is only 1.2 gigabytes. Partial clones have already existed for many years, and they do solve some of the problems we have. So where's the catch? There's two different issues with the current infrastructure. First, clients have to know that they should use partial clones. And second, even if they know, the server would not be able to offload any traffic for those large blobs to a secondary server. This is where large object promises come in. The idea is quite simple. When a client wants to clone a repository, the server will announce a set of promiser remotes to the client. Each of these announced remotes has a URL that the client can use to contact that promiser remote, an optional token that the client is expected to use for authentication, as well as an optional filter that tells the client which objects should be part of this promiser. The client can now decide whether or not it wants to use any of these promises. If it decides to use one of them, then the client performs the initial clone with a filter from the selected promiser. The promiser itself is then stored in the repository configuration. So what does this buy us? The most important point is that we can now have flow where there is more than only one server involved. And referring to that other server is a native part of the Git protocol now. This allows the server to offload some of its traffic to a secondary server. But there's more. Usually, Git talks with remotes by using either the smart HTTP protocol or by using the SSH protocol. But Git also has the concept of remote helpers. You can basically put a binary called git remote something into your path, and from there on, Git will use that binary whenever it sees the something protocol. That opens up a whole lot of opportunities. The server itself could, for example, announce a promiser remote that doesn't use HTTP, but instead it uses something like AWS blob storage to store all of its blobs. If the client knows about this protocol, it will select it, and from there on, it will download any large blobs from blob storage. Much of the server-side logic has landed in Git 250, and more will be released in Git 252. What's still missing here is improvements to the client side, so that the client knows to automatically select promiser remotes. Hopefully, this will be implemented in Git 253 early next year. Large object promises solve only one part of the puzzle. We can now offload large objects on the server side and store them, for example, in blob storage. And furthermore, if configured, the client will learn to automatically omit large objects from clones. But even if all of this infrastructure was ready to go, we have another big problem. We still have to store those objects somewhere on the client side, and the current object format used by Git does not handle binaries well. The question, though, is, does that really have to be the case? Git nowadays has multiple different backends for storing references. Can we maybe introduce a new format specifically to store binary files more efficiently? The problem is that Git has the current storage format deeply baked into it. But that by itself isn't really a good reason. Alternative implementations of Git like libgit2, gogit, and jgit all have the ability to implement custom backends for storing objects. So why doesn't Git have it? I don't really think there is a proper answer. It's mostly that nobody dared to start this project yet. I'm not really saying that introducing pluggable object databases will be without challenges, but it should certainly be feasible, even though it does require a lot of plumbing and refactorings in the code base. So if you had pluggable object databases, how would the new storage format look like? I guess one of the most obvious ideas would be to use something like content-defined chunking. We use a rolling hash function with a window that slides through the data. Every time that hash function outputs a value matching a certain property, we split the object into another hunk. In our example on this slide, that property would, for example, be that the hash needs to be divisible by 7. So we slide our window through the string and compute the hash at every single position. In the case where the result is divisible by 7, we create a new chunk. As we can see in our result here, we have 4 chunks with this specific string. These chunks itself will be content addressable, same as our normal objects. And by doing that, we'll be able to deduplicate chunks that multiple different objects have in common. The nice property of such an algorithm is that you can now insert data anywhere into the file. The specific chunk where you insert the data would now be different, but most of the other chunks would continue to be created the exact same. So even if we insert data at the beginning of the file or into the middle, the majority of chunks should remain unchanged. With pluggable object databases, we can, in theory, replace the whole object storage backend in Git repositories. And in some cases, this might even make sense. For example, a server side may decide to storage objects in a distributed database. But on the client side, there probably isn't too much of a need to replace the full disk format used by Git right now, as it already knows to compress objects with text contents quite well. But Git repositories have the ability to have multiple different object databases connected to them by using the alternates mechanism. The idea is that we would now be able to have 2 object databases connected to a repository at the same point in time, one using the chunked format and one using the normal format. Attached to those object databases is a filter. If an object we want to write is a binary file, we write it into the object database with the chunked format. Otherwise, we write it into the object database with a normal format. Like this, we can easily use different storage formats and thus use whatever format is best for a specific object type. Work is already underway to make pluggable object databases happen. So far, we have landed around a dozen different patch series that prepare the code base for them. The goal of these refactorings is to create a proper abstraction boundary between Git and the actual object format. Until now, there isn't really anything to show yet. All of the work is boring refactorings. But the plans are to finish those refactorings and, once those are done, to officially kick off this project with the design document and the proof of concept. A careful estimate is that we'll have such a proof of concept in Git 253, but a fully working backend to store such large binary files will probably take a couple more releases to materialize. So these are only a small excerpt of the problems that we are currently tackling. Large object promises will make it possible for the server to offload large objects, for example, to blob storage. Furthermore, they will allow a client to learn about whether or not it should exclude some objects from a clone automatically. And pluggable object databases will eventually allow us to store binary files more efficiently on both the client side, but also on the server side. There are more problems with binary files that we'll have to find solutions for, but these issues will probably be a topic for the next year's Git Merge. So that's all for today. If you had thoughts or if you've got any feedback, please don't hesitate to reach out to me via email. Until then, thanks a lot for your attention.